All right, so let's start off with the problem I was asked to cover, which is this one here. The integral, let's move this, I wish this thing went a little higher. By higher, I mean a little higher. That's a little bit. So let's go ahead and look at this following question. I want to find the integral of e to the 3x plus 4 e to the x plus 5 over e to the x dx. And this one might seem, I don't know, not super straightforward. You might think there's a u sub here. I might try letting u equal e to the x, but I feel like I'm not going to really get very far fast, because if I let u equal e to the x, then my du is e to the x, and I don't really have an e to the x times dx. I can't factor one out. When I see a fraction like this, a fraction maybe not, the totally. I'm thinking, if I specifically, when I say like this, I mean, when I see a fraction where there's one term in the denominator and many terms in the numerator, I often think I should probably try just dividing each thing by that term. So I'm going to rewrite this as the integral of e to the 3x divided by e to the x plus 4 e to the x divided by e to the x plus 5 divided by e to the x. And really, you can skip that step and go straight to saying this is going to be the integral of, let's see, 3x minus x is e to the 2x. E to the x over e to the x cancels. And 5 over e to the x, I would certainly rewrite as 5 times e to the negative x. And then these are mostly not too terrible. You could do u substitutions for each of these, but I would encourage you just to think of them as mini u subs. The antiderivative of e to the 2x is e to the 2x divided by 2. The antiderivative of 4 is 4x. The antiderivative of 5 e to the negative x is 5 e to the negative x divided by negative 1, and then plus c. And then if you wanted to simplify a tiny bit, you could write it as 1/2 e to the 2x plus 4x minus 5 e to the negative x plus c. So that's how I would attack that problem. This brings up a similar problem. Sorry, as usual, I've got like a million things to look at here. This brings up, where'd you go? Let's look at a similar but different problem. I've definitely seen this problem show up for a few people. Yeah, let's look at first this one. So let's say we want to find the integral of e to the 3x over 2 plus e to the 3x. So we're going to rewrite this. Well, not rewrite this so much as we're going to try a u sub here, right? This one seems like there might be a good u substitution. I'm going to try letting u equal 2 plus e to the 3x. And my du dx, the derivative of e to the 3x is e to the 3x times 3. I do want to remind everyone, because I think it gets kind of forgotten after a while, when you're finding du, you're literally just finding the derivative of what you've chosen for u. And then we usually put an x over here. Again, there's many ways of doing this. I like to make it so that my right-hand side looks like what I have in my integral. So I would take this e to the 3x times 3 times dx and divide both sides by 3. So that my 1/3 du equals e to the 3x times dx, because I have exactly an e to the 3x times dx. That's going to be my 1/3 du. And become the integral of, I would probably write it as 1/3 over u du. And then the integral of 1/3 over u, or if you prefer, 1/3 the integral of 1 over u du is going to be 1/3 natural log of the absolute value of u. And then we put the u back in. Our u is equal to 2 plus e to the 3x. Welcome.
Good morning.
Good morning. We're doing some midterm review. Thank you.
Oh.
And just in case anyone missed it, here's the attendance form. You can grab it later, whatever. It doesn't really matter. So let's contrast this with a slightly different problem that you might have seen a similar version of, the following. Let's say we want to do the integral of 1 over 2 plus Yeah. Try and think here. Yeah. E to the negative 3x dx. Here, we might try letting u equal 2 plus e to the negative 3x. It's not going to work out. If we let u equal 2 plus, but really kind of that's only the real choice, the only decent choice we have. But if we try that, we're going to get the derivative of this is going to be e to the negative 3x times the negative 3, and then the dx at the end. And we don't have that. So this particular type of integral requires what I refer to as a trick, meaning you probably wouldn't know how to do it unless you've done it one time before. There's actually a couple ways of seeing this. One way of looking at it is like this. So we're going to rewrite it as the integral of 1 over 2 plus, I'm going to write that e to the negative 3x as 1 over e to the 3x. And then I'm actually going to get a common denominator in the denominator. So I'm going to write this as the integral of 1 over 2 e to the 3x over e to the 3x plus 1 over e to the 3x. And then I can write that as 1 over 2 e to the 3x plus 1 over e to the 3x. And then finally, I can flip and multiply and write this as e to the 3x over 2 e to the 3x plus 1. Or, so this is one way of getting there. This is not the way I learned how to get there when I first learned this. You can also do it this way. You can take your integral of 1 over 2 plus e to the negative 3x and multiply the top and bottom by e to the 3x. That's kind of the more of a trick kind of way of doing it. Because when you do that, you're going to get e to the 3x on top. E to the 3x times 2 is 2 e to the 3x, and e to the 3x times e to the negative 3x is exactly 1. Either way is fine. This to me, this work feels like less steps, but this might feel a little more like you would understand how you would make that leap. Right? Like this kind of feels like, oh, you just need to have seen it before to know to do this. Either way, we're getting to the same integral, this or this. And now we can totally do a u substitution. We're going to let u equal the denominator, 2e to the 3x plus 1. And our du is going to be 2e to the 3x times 3 dx. So 1/6 du is going to equal e to the 3x dx. And then we can rewrite this integral as the integral of 1/6 du over u. You don't need to bring the 1/6 out. We can just think of it as coming out. We're going to get 1/6 natural log of the absolute value of u plus c, which is going to equal 1/6 the natural log of the absolute value of our u, which is 2e to the 3x plus 1. C. It's a little tricky, but it might come up. All right, let's. Sure. Sorry, all over the place. Where did you go? I feel like I'm always losing things. I'm like, oh yeah, there it is. So I think really, I think practicing some integrals is probably our best use of time. I'm good. Okay. So. And we'll do definite and indefinite. Let's look at the following. Sure. So let's try the integral of 1 over the square root of x times 1 plus the square root of x. And I should point out, this is written kind of in this way on purpose. Right, someone could have given you this problem where the bottom was distributed, where it was 1 over the square root of x plus x. And that's a much less nice way of giving it to you. when it's written this way, it's kind of like it's written with a hint in the story. It's written this way, you might think, well, I might have a choice for you. I might try letting u equal the stuff that's inside of parentheses, like 1 plus the square root of x. And then our du is going to be, though the derivative of 1 is 0, the derivative of root x is 1 over 2 root x. Or you can write it as powers, right? This is x to the negative 1 plus x to the positive 1/2. And the derivative would be 1/2 x to the negative 1/2 dx. Either way is fine. So then looking at this, I see in my integral, I've essentially got what I need. I have a 1 over root x. I just need to get rid of that 2. So 2 times du is equal to 1 over root x dx. And we can rewrite this integral as well, the dx over root x is going to be a 2 du. So we're going to have the integral of 2 du over u. We're getting a lot of something over u. That happens often. So this is going to be equal to 2 natural log of the absolute value of u plus c. And then we're going to get 2 natural log of the absolute value of 1 plus the square root of x. That's it. Oh, there we go. Nice. Oh, yeah. Okay. Sorry, I found the thing that's before. Yeah.
Why do you not use square root of x plus x as the u?
So that's a good question. So what if I had? So what if we looked at this one and said u equals the square root of x plus x? So then our du would equal, let's see, the derivative square root of x is, again, 1 over 2 root x plus 1 times dx. And at least when it's written this way, I'm not really seeing anything like that. I might be able to manipulate this. I might be able to write this as, like, I don't know, 1 over 2 root x plus 2 root x over 2 root x. But it just seems like if I'm having to work that hard for my du dx, there's probably a better way of doing it. Additionally, the fact that the problem was given to me in this format is implying that there's probably some choice we want to make because it's written that way, right? Someone might give you this problem like this. That would be cruel because it's written in such a way that it's really, really hard to see what you might do. Whereas this is a more reasonable type of problem to write. But yeah, so I mean, the answer really is the reason I wouldn't choose u to be root x plus x is because it doesn't really work. I'm not getting my du showing up, which is what we need to happen. All right, let's look at following. Sure. How about this one? Why don't you all try this one? The integral of x squared times sine of 4x cubed plus 6 over cosine of 4x cubed plus 6. Give you a couple minutes to work on that one. So what could we choose for u? Well, let's go simple. We could probably choose 4x cubed plus 6. It's certainly valid. It's stuck inside a couple of different functions, and importantly, its derivative is there. The derivative of 4x cubed is 12x squared. Now, when I say the derivative is there, I really mean up to a constant multiple. So then I've got an x squared, I don't need the 12. So 1/12 du is equal to x squared dx. So if I do that, here's what I'm going to get. It's going to be equal to 1/12 the integral of sine of u over cosine of u du. Right, because the x squared dx, whoops. The x squared dx was my du. My 1/12 du. But now we're faced with integrating sine of u over cosine of u, which you could think of as tangent, although it's not particularly helpful to do so. If we're going to integrate this, we actually need to do another u substitution. Now, since I've already used the letter u, I shouldn't use it again. So I typically use w if I've already used u. So I'm going to let w equal, ooh, which one? All I heard was sine, but you might have said cosine. Did you say sine or did you say cosine? Cosine, okay. I would also pick cosine because it's in the bottom. So w equals cosine of u, and our dw is equal to negative sine of u du. So our negative dw is positive sine of u du. So I'm going to rewrite this as 1/12 the integral of negative dw over w. And I probably bring out the minus sign. So I write it as minus 1/12 the integral of 1 over w dw. And again, we're integrating a 1 over our variable. So we're going to get negative 1/12 times the natural log of the absolute value of w, which is then going to be negative 1/12 times the natural log of the absolute value of cosine of u, which is plus c, which is then going to be negative 1/12 natural log of cosine of the absolute value of cosine of 4x cubed plus 6. This does bring up kind of an important observation that if you're integrating tangent, you actually get the natural log of cosine. So let's make a similar problem just a little bit easier. If I wanted to find the antiderivative of tangent of x, we would totally write it as the antiderivative of sine of x over cosine of x and do the same sort of substitution we just did. We would let u equal cosine x, du would be negative sine of x dx, so negative du would be positive sine of x dx, and this integral would become the integral of negative du over u, which would be negative natural log of the absolute value of u, which would be negative natural log of the absolute value of cosine of x. And this is something that comes up often enough that you probably want to know it. It's probably worth memorizing. I should also point out that this is not the only way people write the answer. Some people write it like this. Some people like to take that negative 1, and bring it up as the power of cosine of x. But then cosine of x to the negative 1 is just the reciprocal of cosine, which is secant. So another way of writing the antiderivative tangent is the positive natural log of the absolute value of secant of x. It comes up occasionally. In the same sort of vein, so these are integrals that I feel like you probably going to see, you probably maybe have seen. They're in section 8.5 or whatever, like that one section that's in chapter 8 that you've looked at with the trig stuff. So here's another one that you might want to be aware of. The integral secant of x is actually an interesting integral for lots of mapping reasons, but I shouldn't get too into that because it's not that important. the way you do this, there's a trick. You don't need to know this trick, but you do probably need to know what this integral is. So here's the trick. We're going to multiply the top and bottom by secant of x plus tangent of x. The reason we do this is because if we multiply at the top, look what we get. We get, and I'm going to actually switch the order, secant times tangent, so secant x times tangent x, plus secant x times secant x, which is secant squared x, over secant x plus tangent x. And now we have a really, really nice choice for you. What's the derivative of secant? Secant tangent. What's the derivative of tangent? So look, the top is exactly the derivative of the bottom. So we're going to make the choice of letting u equal secant x plus tangent x. And then your du is exactly secant x times tangent x plus secant squared x dx. So this exactly becomes equal to the integral of 1 over u du, which is the natural log of the absolute value of u, plus c, which is going to be the natural log of the absolute value of secant x plus tangent x plus c. That's not one you want to have to derive every time. It is definitely one that if you need to know it, you should just memorize it. You might wonder how someone came up with this, like how did they figure this out? Really, they discovered the integral secant of x a different way. And then later on, someone's like, oh, you could just, like, they saw what the answer was. And they're like, oh, well, if you take the derivative of that, right? If you took the derivative of this, you would exactly get 1 over secant plus tangent times secant x tangent x plus secant squared x. So they're like, oh, you could do this trick. But someone found the integral first, and then they kind of discovered the trick later. Kind of neat. Let's look at some definite integrals, like following. Yeah, this one. Let's do this one because I think this one illustrates some important things. So let's find the area bounded by y equals x squared on the right, y equals 8x on the left, and above by y equals 16. Okay. You don't have to draw this, but it's almost always a good idea to draw it. I would say it's always a good idea to draw it if you've got more than 2 curves going on. Like if it's just 2 curves, you usually can be like, okay, I can find where they intersect and just do the top one minus the bottom one, but usually you don't have to draw it. This one I feel like I need to draw. So I know what these basically look like. I know that y equals x squared is my usual parabola. Y equals 8x is a straight line. Now the thing I don't know is like y equals 16. So I was going to draw this so that these intersected, but then how is this important? So I should maybe think about where things intersect. So if I set 8x equal to x squared, I can find where my line or my parabola intersect. So 8x minus x squared equals 0. Factor out an x. So you're getting x equal to 0 and x equal to 8. Here's the problem. X equal to 8 goes with y equal to 64. And that's way higher than my upper bound. So these are going to intersect somewhere way up high over here at x equals 8 and y equals 64. But y equals 16 is much lower than that. In fact, we could totally find this one here, right? If y equals 16 is intersecting y equals x squared, well, then 16 equals x squared, and you're going to get x equals 4. Similarly here, if this is the graph y equals 8x and y equals 16, well, 8x equals 16 is going to give me x equal to 2. So we're not finding where they intersect up here because we were told specifically we're bounded by y equals 8x on the left, y equals x squared on the right, and above by y equals 16. So we're looking at this area here. And so if I'm going to try and find the area that's using vertical cross sections, I'm going to have to do two integrals because over here, the top function is 8x and the bottom function is x squared. And over here, the top function is 16 and the bottom function is x squared. That's doable. It's just we have to use two integrals. So the area is going to equal, well, the integral from 0 to 2 of the top minus the bottom, plus here the integral from 2 to 4 of the top minus the bottom. And that's how we can calculate this. Now, it's worth mentioning here that someone might ask you to do this in a different way. Instead of using vertical cross sections and doing two integrals, we could do it using horizontal cross sections. So I think of the same picture. I'm not going to draw it quite as precisely because I don't really need to. Right? If I'm looking at the same sort of region here. And now if I want to use horizontal cross sections, I'm thinking, okay, I'm going to do the integral from as low as 0 to as high as 16. And then instead of doing top minus bottom, I'm going to be doing right minus left. Well, my right-hand function, if I solve for x, it's going to become x equal to the square root of y. And my left-hand function, which was y equal to 8x, if I solve for x, I'm going to get x equal to 1/8 y. So it's going to be the square root of y minus 1/8 y. Either way of doing this is probably fine. I should say, either way of doing this is definitely fine. I couldn't really say which one I would prefer to do. I would probably do this one because it feels like I have to do less writing here. But really the point of this is that you can kind of do it either way. Someone might be specific. Someone might say, find the area of this using horizontal cross sections. But they might specify that you have to do it using horizontal, which I always find to be a little bit more difficult. Well, let's see what we get. The antiderivative of y to the 1/2 is y to the 3/2 times 2/3. The antiderivative of 1/8 y is 1/8 times y squared over 2. And we're evaluating from 0 to 16. It's going to be a little messy. I would probably, so again, on an exam, if you don't, especially if you don't have a calculator and you have kind of gross numbers like this, I would stop once I plugged it in. I would say, all right, I'm going to get 2/3 times 16 to the 3/2 minus 1/16 times 16 squared minus 0 minus 0. And then if I had time, I would simplify it further. This one actually, so I was worried about the 16 squared, but luckily one of those 16s is going to cancel out real nicely with the other 16. So I don't really have to do 16 squared. So I'm going to end up getting 2/3 times 16 to the 3/2 is 4 cubed, which is 64, minus 16. And let's just leave it there. One could simplify that. One does not simplify it. But, you know, I'm compulsive, so there, 80/3. Definite integrals are a thing. We can do more of them. I feel like they're worth practicing. Add another one. Sure. Oh, that's a good one. Yeah. Let's do the following. Let's say I want to find the antiderivative of, or sorry, the integral from, I don't know, say 4 to 7 of 1 over x times the natural log of x squared. I don't know how to anti-differentiate that. It probably is going to require, so really at this juncture, there's only really two things we know how to do other than just straight up anti-differentiate a function. The two methods we have are kind of simplify it in some way, right? Maybe do some dividing, maybe multiply by an e to the 3x, right? Whatever you've got. The other method we have is U substitution. So if you see something that doesn't look like you can just find the antiderivative right away, you should think, can I simplify it? No, I can't simplify that. Or can I try a U sub? Those are really our only options at this point. Okay, there's a third option, which is, does it have a nice geometrical shape? Like, is it the part of a circle? Right. So I should point out, like, if you see this, there is a third option. Right, but typically our options are either simplify, U sub, or maybe it's a circle or part of a circle. Right, I would not be surprised if someone asked you this question on your test. So find the area, and you were supposed to know, oh yeah, that's going to be a quarter of a circle. Of radius 5. So look out for that. If you see something like this, square root of something squared minus x squared, that's what you're going for. But here, it's a U sub. And we're going to let u equal the natural log of x for the usual reasons. Its derivative is in there and it's stuck. Our derivative, du dx, is 1 over x. So our du is 1 over x dx. I exactly have that. I have a 1 over x dx. So when you're doing u sub with a definite integral, the choice I would encourage you to make is to change your limits of integration. So I'm going to rewrite this, and this is an x equals 4 to an x equals 7. I'm going to rewrite this as the integral. Let's see, my 1 over x dx becomes my du, and my 1 over natural log of x squared is now 1 over just u squared. And my new limits of integration, instead of being x equals 4 and x equals 7, are going to be, well, u is equal to natural log of x. So if x equals 4, u is equal to the natural log of 4. And if x equals 7, u is equal to the natural log of 7. And the nice thing about this is you don't have to change back once you've done the antiderivative. So we can rewrite this as the integral of u to the minus second from natural log of 4 to natural log of 7 du. And then the antiderivative of u to the negative second is u to the negative first over negative 1. Or as I would probably write, negative 1 over u from natural log of 4 to natural log of 7. And then we can plug in and get negative 1 over natural log of 7 minus negative 1 over natural log of 4. Which I might write as 1 over natural log of 4 minus 1 over natural log of 7. Now, some people don't like doing it this way. It's totally fine. The other option, if you prefer, is to instead say, I'm going to just do the integral and leave my limits alone from x equals 4 to x equals 7 of 1 over u squared, or u to the negative second. If you do it this way, I really recommend writing x equals and x equals, so the person who's reading your work knows that you thought about the fact that you weren't changing them. And then we get to differentiate, we get the same thing. We get u to the negative first over negative 1, which is negative 1 over u from x equals 4 to x equals 7. And then we plug back in that u is equal to the natural log of x from x equals 4 to x equals 7. And now I think you can see how it's going to be the same. So either way of doing it this way is fine. Just make sure you're careful. If you change the limits of integration, which I recommend, then you don't have to change back to the end. But if you don't change the limits of integration, then you do need to change back to x's and then plug in the appropriate values. Seem good? Okay.
One question.
Yeah.
Can we put the can you give us the steps for the integral of the
Sure. Well, kind of. So if I wanted to find the antiderivative from 0 to 5 of the square root of 25 minus x squared, here's the way you were supposed to do this problem in this class. Here's all the work you can show. Oh, that's a circle. So then we draw the circle, but really, this is the top half of a circle, right? Because if y equals the square root of 25 minus x squared, y can't be negative. Y only is positive. So here's my circle. Center is the origin. Radius is 5. And then I know this integral is going to equal the area under the curve from 0 to 5. So I'm starting at 0 and I'm going. So that's going to equal 1/4 the area of the circle, which is going to be 1/4 times pi times 5 squared. I know that wasn't your question, but the real answer to your question requires a method of integration that we don't want in this class. So the real answer is you have to do what's called a trig substitution, where you let x equal to 5 sine theta. I know that sounds maybe a little out there, but if you really want to know, I can show you an office hour sometimes.
Oh, no, I just thought I was going to do an example.
No, so no one's going to ask you to find the antiderivative. They might tell you the antiderivative. So someone could say, for example, there are a couple problems like in the homework I saw where they're like so actually, yeah, let's make up something. So I've definitely seen a problem. Actually, let me instead of trying to make up something, let's actually just look at it so I don't make up something wildly insane. No, it's everywhere. I wish this table was just a tiny bit bigger. I know there's a whole table over there, but it feels way over here. Let's see. 1 second. Yeah. Oh, in fact, yeah. Okay, that's less exciting. But sure. So here's an example from the homework. So actually, we can use the example here. Where did you go? I'm an old man who loses things all the time now, apparently. Sorry. Really? Where was the example? I literally just wrote it. Why did it disappear? I don't know. Okay, so we could do something like use the fact that this integral from 0 to 8 of the square root of 64 minus x squared dx is equal to 16 pi to calculate the following. So what are they trying to get us to do here? How, so yes, but why do we get to do that? Right? More general. So yes. So let me, so yeah, I'm going to agree with that, but I'm going to say a little more. What if instead I said the following? So similar question. So yes, I would say this is definitely equal to 2 times 16 pi. And then kind of by extension, if you know that the integral from 0 to 8 is 16 pi, and the integral from -8 to 8 is 16 is twice that, you could also say the integral from -8 to 0 is also 16 pi. You could also say because it's the other half, or it's the other quarter of the circle, right? What if I said this instead? I know that the integral from 0 to 8 of, sure. So I was trying to make up something that's like not super easy to do, but then I'm just like, it's going to be a lie because I don't actually know what it's equal to. Let's say that we had the integral from 0 to 8 of x to the 6 minus x squared dx, and it was equal to, it's going to be terrible. I don't actually want to calculate it. Let's just pretend it was equal to 1,000. I know it's not, but let's say it is. Pretend. What if I asked you to calculate this? What should that be equal to? Right, but why? But why do, and the question I want to ask is, why do we get to double it?
Oh, because it's an even function.
Right, because it's an even function, exactly. So this is going to equal 2 times 1,000 because the function you're integrating is in fact even, which is the same thing that's true up here. This is also an even function, right? It has that even symmetry, so you're also welcome to double. It also is the top half of a circle, so you can use that fact as well. But that's kind of what I was going for. Is that even functions, you can totally just double them to get the area on the left and the right. I feel like there was a more interesting question. Yeah. Okay, there we go. This is a more interesting one. So let's say we have the following: the integral from 0 to 2 of 5x cubed times the square root of 4 minus x squared dx is equal to 64. Sorry, that's a 15x cubed, not a 5x cubed. So this is given. Can we calculate the integral from -2 to 0 of 15x cubed times the square root of 4 minus x squared? Well, we can, not the same way as before.
Why isn't this one like an odd function?
It is an odd function.
Like 0?
It's not, well, something will equal 0, but not that. So it is true that this function f of x equal to 15x cubed times the square root of 4 minus x squared is odd.
Oh, it's going to make this 64.
Right. So there's two things you can say. Definitely this integral is -64. And you can also say that the integral from -2 to 2 of 15x cubed times the square root of 4 minus x squared is definitely equal to 0. Essentially what we have, and I don't know exactly what this function looks like, but it looks something like, let's see, when you plug in 0, you get 0. When you plug in 1, you get some large number. When you plug in 2, you also get 0. So this function looks something like that, where this area here is totally going to cancel out this area here. A question I've often seen or like to ask on tests is to calculate this. I don't know how to integrate that at all. Neither do you, because it's probably not actually integrable, because I made up something that's stupid. But what we should see here is that we're going from -3 to 3. That's often a clue, although not always, but it often can be a clue that you might be having an odd function. So we should check to see if the function's odd, and then if it is, say that the answer is 0. If it's not, we're screwed because we can't integrate this. But typically, if you see something that looks super kind of odd, meaning strange, it might actually be odd, meaning having that symmetry. So let's check. Does f of -x equal -f of x? Well, f of -x is going to be -x squared times sine of -x over 1 plus -x to the 6th power. And this is where you have to know that sine is in itself an odd function. Sine has that odd symmetry. So sine of -x is equal to negative sine of x. So then we can rewrite this as, well, -x squared is positive x squared. Sine of -x is negative sine of x. And then the bottom is 1 plus x to the 6th. Oh yeah, that's definitely equal to the negative of the original function. So this function is odd, which means this integral is equal to 0. So yeah, if you see something that looks funky, but the limits of integration are opposite values, it's probably a good bet that you've got something that's going to equal 0. Let's see, what else was on my mind as far as things you might want to look at? I feel like there's a lot of things that you could think about. Oh yeah, let's go back. So we can certainly do more integrals if you want, but I feel like we should take a minute, talk about a couple logarithmic differentiation problems, just because it's probably going to come up. So let's say you're like, no, probably not. You don't like them? That's all right. I don't like them either. So let's say we had something like, let's make it not too bonkers. Yeah, but let's say it's something like y equal to x cubed plus 2 to the x squared power. And I want to find the derivative of that. So we're going to take the natural log of both sides. And when you see variables to variables, that's always what we're thinking. Take the natural log of both sides. And the whole point of taking the natural log of both sides is so that that power x squared gets to come down in front. So we have the natural log of y equal to x squared times the natural log of x cubed plus 2. And then we can differentiate both sides. 1 over y times the derivative of y is equal to, I got to use the product rule here. It'll be 2x times the natural log of x cubed plus 2 plus x squared times the derivative of the natural log of x cubed plus 2 is 1 over x cubed plus 2 times 3x squared. We're almost done. Multiply both sides by y. You might simplify this a little bit. 2x times the natural log of x cubed plus 2 plus x squared times 3x squared is 3x to the 4th over x cubed plus 2. And then finally, and you could have done this all in one step, replace the y with what it's equal to. So that y prime is equal to x cubed plus 2 to the x squared power times all of that. It's not too terrible, but it is a process. So what other kinds of things? Oh, that's a good question. So here's a question that's on this practice test that I think is worth looking at. True or false? Which always feel terrible in math tests. Like, I don't know. I feel like a true or false section is always like, really? So the integral of e to the x plus natural log of x equals the natural log of e to the x plus natural log of x. How would you check this? Do you know what the integral of e to the x is? Yeah. Do we know what the integral of natural log of x is? That's the derivative. We don't yet, we will learn it eventually, but we don't yet have the tools to integrate natural log of x. So we can't check this by doing the integral of this. What could we do to check it instead? Right. So let's see. And typically this is what's intended if they're asking if an integral is equal to something else, take the derivative of something else. The derivative of the natural log of e to the x plus natural log of x is going to be 1 over e to the x plus natural log of x times the derivative of that, which is e to the x plus 1 over x. I'm pretty sure that's not going to end up equaling e to the x plus natural log of x. Seems like a big jump to get there. So no, this is false. Ooh, I like this one too. So here's one you all should do. True or false? The derivative of e to the x cubed equals e to the x cubed. All right, what do you guys think? True or false? It's not true. So that's part of the answer, but if we take the derivative of e to some power, the derivative of e to the stuff is e to the stuff times what? The derivative of the stuff. So the chain rule says this is the derivative. So whenever you take the derivative of e to the function, you get e to that function times the derivative of that function. Let's look at, in the same sort of vein of kind of going back a little bit, let's look at a exponential growth or decay problem. So let's say we have 80 grams of a radioactive element. And we observe that after 5 days, only 30 grams remain. First question. What's the half-life of this substance? So the half-life is how long it takes until we get to 40 grams. So, but the half-life is definitely an amount of time, not radioactive material. The thing I would say to myself first off as I was doing this is, okay, great. The half-life is how long it takes to get to 40. I know that's going to be less than 5 days, right? Because in 5 days, there's only going to be 30 grams left. I really like to think about the context of my answer. Now, I know I haven't found the answer yet, and the answer is not actually going to be super contextual in that it's going to be something with a logarithm in it. So we're not going to really be able to see if it's less than 5, but we could use a calculator. So whenever I have a problem like this, I always like to draw a little table of what time it is and how much stuff I have. And I know at the beginning, I have 80 grams of stuff. And then I know that 5 days later, I have 30 grams of stuff. And if you have 2 data points, that's always enough information to find all the constants in your model, which is y equals c to the kt. You can either do the work, or we can just know that c should be the amount you have at time 0. So we're going to say that c is equal to 80. So really we have y equals 80 e to the kt. The way you get that is by just plugging in 0 for time and 80 for y, and getting c times 1 equals 80. To get the other constant k, we're going to plug in 30 for y and get, and plug in 5 for t. Hi, you're here for Co-16B? You're here for Co-16B? Oh, no. Every time. All right, so anyway, solving for this, I'm going to isolate the e to the stuff. So I have 3/8 equals e to the 5k. We're going to take the natural log of both sides. Natural log of 3/8 equals 5k. And finally, dividing both sides by 5, k is equal to the natural log of 3/8 divided by 5. I would observe that this value is negative because the natural log of 3/8 is a negative number. If you don't think of it that way, you can think of it as the natural log of 3 minus the natural log of 8, and then it's a little more obvious it's a negative number. Or you can think of the graph, right? The graph is definitely negative when you're before 1. Okay. The only reason I make that point is because if it's exponential decay, your k value should be negative. So we have our model now, y equal to 80 e to the natural log of 3/8 divided by 5 times k. And now, to find the half-life, we're going to set something equal to 40. Which thing? The y or the t? Oh, sorry, that's the t there. Apologies. What do we say equal to 40? The y or the t?
Y.
Right. And we're going to try and find how long it takes to get there. So setting y equal to 40, we're going to get 40 equal to 80 e to the natural log of 3/8 over 5t. Divide both sides by 80, so you get 1/2 equal to e to the natural log of 3/8 over 5t. Take the natural log of both sides. The natural log of 1/2 equal to the natural log of 3/8 over 5t. And then multiply both sides by 5. Divide both sides by 3/8. Natural log of 3/8. And that's, without a calculator, kind of the best way you can express your answer. Something to say about this? No, not really. If you've ever taken chemistry, you might recognize this, like the half-life is always the natural log of 1/2 divided by the K value. If you haven't taken chemistry, congratulations. Like, it's a hard class. And I certainly avoided it. Chemistry's fine. It's got good things in it, but I avoided taking it because I didn't want to take it. So yeah. The other thing we might ask about a question like this is, which is less exciting, is how much radioactive material remains after 10 days. And it's not very exciting because all we're going to do is plop 10 into the formula. Now, there is a way you can figure this specific question out without actually doing any of the work, or without doing much of the work. We have our little table here. With those two data points. And now here's the thing that's true about radioactive growth or decay. Any specific time period always multiplies the amount of stuff you have by the same amount. So when someone talks about radioactive growth or exponential growth or radioactive decay, people talk about the doubling time being the same, meaning it always takes the same amount of time to double, or the half-life time. It always takes the same amount of time to be 1/2. But it's also true for any multiplier, meaning if you look here, it takes exactly 5 days for there to be 3/8 as much stuff. And if they're asking how much material is there after 10 days, the same thing is going to happen. You're going to end up multiplying this by 3/8. 30 times 3/8 is 98. Now that doesn't seem very, like, I don't know. It's not like, it doesn't feel very rigorous. You're just making stuff up, kind of. It is true though. Now, here's how you can see it in the actual work we did. If you take our model, which was y equal to 80 e to the natural log of 3/8 over 5 times t, and if you plug in t equal to 10, you're going to get y equal to 80 times e to the natural log of 3/8 over 5 times 10. Which you might say that looks pretty terrible to try and deal with. But let me show you how this is going to work out kind of nicely. So 10 over 5 is 2. So I can rewrite this as 80 times e to the 2 natural log of 3/8. Then that 2 can come up here as the power on 3/8. So I can rewrite this as 80 times e to the natural log of 3/8 squared. But hey, look, e to the natural log of some stuff is just the stuff. This is 80 times 3/8 squared, which is 80 times 3/8 times 3/8. So each period of 5 days multiplies the amount of stuff you have by a factor of 3/8. We did it once to get to 30. We're going to do it again to get to 9/98. Kind of neat. Kind of. I mean, So if someone asked you how much stuff there was going to be after 20 days, you can be like, well, I'm going to multiply by 3/8 4 times instead of doing this work. This work also works just fine, but it's just kind of an interesting observation. Okay, what other things should we talk about in the last 15 minutes we have here? Well, let's do an implicit differentiation problem. I'm just trying to kind of cover all the bases of stuff that could be on this first midterm for people who are taking this first midterm in longest last name ever class. I should really practice trying to say it because like I'm sure I could say it if I just looked at the letters and if I sounded it out like I was, a younger person, but see long letters. Okay, let's try this one. Let's find the equation of the line tangent to x squared plus e to the xy equal to y cubed plus 9 at the point 0, -2. All right. So there's two different types of implicit differentiation problems typically. This is the kind that I like better, where you don't actually have to find the derivative as a function of y and x. So here's what we're going to do first. Differentiate. So the derivative of x squared is 2x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So I'm actually going to leave and we'll do it another step. The derivative of y cubed is going to be 3y squared times y prime plus the derivative of 9 is 0. And then let's do one more step here. The derivative of x times y, we have to use the product rule. It's going to be 1 times y plus x times the derivative of y. So there's two ways we could go here. The way we should go, since I should say, if this problem said, instead of find the equation of the line tangent, if the problem said find y prime, then we would have to do the work of actually solving for y prime. So in fact, we'll talk about that over here in a second. But here, since we're trying to find the equation of the line tangent to this function at this one particular point, we only care about finding the slope of the tangent line at that point. So we can go ahead and plug in that point right now. So we're going to plug in x equal to 0 and y equal to -2. So if I plug in x equal to 0, I'm going to get 2 times 0 plus e to the 0 times -2 is 0. Y is -2. X is 0 equal to 3 times -2 squared times y prime. So let's see, that's 0, that's 1 times -2, so I get -2 equal to 3 times 4 y prime. So I'm getting y prime equal to -1/6. So for this tangent line, we're going to get y, well look, they even gave us the y-intercept. How nice is that? Y equal to -1/6 x plus -2. So if you're being asked to find the equation of the tangent line, definitely after you take the derivative of both sides, if it's implicit, just plug in your points because it's usually less algebraic work. On the other hand, if the problem had been, here's this equation, find y prime, then you'd have to take this equation and actually solve for y prime. All right, let's do a different problem where we have to do that because I think it's worthwhile. So let's see. So let's say we were given, I don't have to make it work. Let's say we're given find dy dx or y prime, whichever way you want to write it, for the following function. Y to the 4th plus x squared y equal to 9e to the y squared plus 2x. So again, this is really just after you do differentiation once, this is really mostly an exercise in algebra skills. So the derivative of y to the 4th is 4y cubed times y prime. And whenever you're differentiating something with y in it, you have to multiply by y prime. Derivative of x squared y is going to be product rule, 2x times leave the y alone, plus x squared times the derivative of y is the derivative of y. This 9e to the y squared thing looks terrible. It's going to be 9 times the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of y squared is 2y times y prime plus 2. And then I typically make a point of underlining or somehow noting all the terms that have a y prime. I should point out in the previous problem, sorry, how do I just make the papers disappear? It's like a magic skill. Okay, in the previous problem, if I was doing that at this point, before I could kind of group the y primes together, I would really need to distribute this term to each of these so I could separate the term that has a y prime from the term that doesn't have a y prime. It's not necessary here. So here, I'm going to bring all my y prime terms to the left. And I think you could probably also factor out the y prime at the same time. Like, I don't think it's too algebraically challenging. Saying it, on the other hand, is. So I might write this as 4y cubed plus x squared minus 9 times 2 is 18e to the y squared times y. And then all of that is multiplied by a y prime. Or you can do it in 2 steps. Equals 2 minus 2xy. And then finally, divide by all this stuff over here. So that y prime equals 2 minus 2xy divided by 4y cubed plus x squared minus 18e to the y squared times y. Like, I'm trying to think if there's anything that looks really also terrible. That's interesting. So let me, I will, so I do see one problem on this practice test. It seems interesting to me. I don't love it, but it's fine. So here's a question that's on this test, which I think is kind of wonky on this practice test. Find the derivative of 2 to the f of x times g of x. That can be stalked. Like, people are like, are they done yet? Are they done yet? It's 10:15. I have at least 5 more minutes. Not really. I have 5 minutes. I was going to end kind of early. So, but this is a question on the test where and they're not giving you f of x times g of, or g of x. They're just saying, find the derivative of this, which seems a little funky, but fine. So if I was doing this, I would probably do something first. First, I would write it as y equal to 2 to the f of x times g of x, just because it feels better to do it that way. And then I would say, all right, my derivative dy dx or y prime, whichever way you want to write it. You could do this a long way, but we do have a rule for when your base is a constant to a power, that's a function. We know that the derivative of 2 to the x is 2 to the x times the natural log of 2. And the derivative more generally of 2 to the stuff is 2 to the stuff times the derivative of the stuff times the natural log of 2. So here, the derivative of 2 to the stuff is going to be 2 to the stuff times the derivative of the stuff times the natural log of 2. And then to take the derivative of f of x times g of x, we have to use the product rule. So this is going to be 2 to the f of x times g of x times f prime of x times g of x plus f of x times g prime of x times the natural log of 2. But it's kind of a weird question, right? Because like you wouldn't expect, like if I saw this on a test, I would feel like I would get thrown off. I'd be like, wait, what's f and what's g? But they're not giving you that, and so they're not expecting you to know it. They're just expecting you to kind of use the formula until you're kind of have written as much as you can. There's nothing more we can do here. We don't know f, we don't know g, we don't know f prime, we don't know g prime. But we shouldn't leave it like this, where you have f times g prime, right? We should use the product over there. Yeah, I feel like, yeah. I feel like let's call, oh, question, yeah. Yes, of course, anytime. I take requests. Which one? Oh, sure, yeah, totally. So we're trying to find the derivative of that. So we got y equal to the natural log of x over x squared plus 1. Cool, thank you. So if I was trying to find the derivative of this, I personally, and I would encourage you all to first simplify. So if you have the natural log of a fraction or a product, I would encourage you to use the log rules and say this is the natural log of x minus the natural log of x squared plus 1. And then we can take the derivative of this using our log rules. So the derivative of the natural log of x is 1 over x. And the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which I would leave as is. Now, let's say we forgot that rule. That we forgot that you could simplify a logarithm. This one you could also do not too terribly straight, just straight away. Now, again, if I was writing a problem like this on a test, I would make it more terrible. I would give a problem like this. Y equals to the natural log of x cubed times the square root of x squared plus 1 over sine of x times, I don't know, e to the 2x. With the real strong intent that you would have to break it up into 4 different pieces. So if you see something where it's natural log of some real hot garbage over here, they really, really, really want you to break it up using the log of a quotient is the log of the first thing minus the log of the second thing. And the natural log of a product is equal to the natural log of the first thing plus the natural log of the second thing. However, if you saw something like this and you didn't remember those rules, you could do this one without too much trouble. The derivative here would be 1 over the stuff times the derivative of the stuff. But I think you can agree that's a lot more work than we did up here. Right here, I'm going to do, okay, I'm going to flip this over and get x squared plus 1 over x. And then quotient rule, bottom times the derivative of the top minus top times the derivative of the bottom, all of the bottom squared, right? You don't want to do it this way. You could, but definitely, the intent of a problem like this is to simplify it first and then differentiate. Yeah, good question. Yeah.
I have a question. When it tells us to find the area that owns the curve, is there any way to know which function is on top and which function is on the bottom without drawing the?
Yes. So let's say, for example, now this is going to be back. Oh, nice. Okay. So let's say, for example, we wanted to find the area between these two curves, f of x equal to, let's say we had x squared minus 6x and g of x is equal to, sorry, x squared minus 6x. Actually, I wanted the negative of that. And then, yeah, sure. And then g of x is equal to, sorry, I'm trying to make it not terrible. Let's say the g of x is just equal to x. Normally I would draw them, but we're not going to. So first, find where they intersect. So setting these equal to each other, we're going to get, let's bring everything over to the right, to the left, sorry. So 6x minus x is 5x minus x squared equal to 0. You're getting x times 5 minus x equal to 0. You're getting x equal to 0 or x equal to 5. So these intersect at 0 and 5. So I'm going to pretend like I don't know. So one function's on top, one function's on the bottom. I don't really know. Here they intersect at 0, 0 and at 5, 5. I've drawn them this way. I don't actually know which one's on top. But here's what I do know. If they only cross at these 2 points, between those 2 points, one of them is always above the other one, right? They don't cross again. So if I can just find out which one's on top at one spot between them, I know it's always on top. So pick any point between 0 and 5. Pick, say, x equal to 1. f of 1 is -1 plus 6, which is 5. G of 1 is +1. So that's bigger, it's on top. And that'll always work.
Okay, we can just pick a point in the middle and like plug it in.
Right, exactly. Now, if they cross more than, if they have more than 2 intersection points, then you have to check something in each one. So like if you had some function like this, where they cross like here, here, and here, then you'd have to check a point here and see what's on the top and a point here. And you have to break it up into 2 intervals. Yeah, good question. You're welcome. All right, call it a day.